Hello, and welcome to Chapter 6, Section 3. This is my second time filming this video because the first time I did it, it didn't save. The whole video disappeared. It was very upsetting. So here I am. Hopefully the second time around I remember to say everything because now I can't remember what I've said and what I haven't. Yikes. Okay, here we go. So this section, I'm actually splitting this section up into two parts. So the full section is going to be binomial and geometric random variables, but today I'm only going to talk about binomial random variables. And so before I even get into it, I want to start off with an example. So when we talk about binomial random variables, I want to demonstrate like what the situation is going to look like. So let's say we are trying to find the probability that when I roll a die 3 times, I want to see how many times I can actually get a 4 just once, which is really like me saying, what's the probability I land on a 4 the first time, and then the other 2 rolls I get not a 4. Or I can get the first roll is not a 4, the second roll is a 4, and then the third roll is not a 4. So basically like the different ways I can roll a 4 just once out of the 3 tries. The third way, I would just get the 4 the last time with the first 2 not being 4s. Okay, so I kind of wrote this out as you can see here so that you can kind of see the type of probability we're trying to find. Because when I ask about a probability of rolling a 4 just once out of 3 tries, like we have to take into account all the different orders that we can do this in. And so if you think back to when we first started doing like probability in last chapter, we talked about how when we take multiple actions, we have to multiply probabilities together. So if I were to roll a 4 on the first try and then the second and third were not 4s, the probability would look something like this. 1/6 times 5/6 times 5/6, because the 1/6 is the probability of rolling a 4. Then on my second roll, I want to get not a 4, and so there's 5 different ways to do that. So 5 out of 6 times another 5 out of 6, because for my third roll, I again don't want a 4. All right, or the other situation, so remember OR formulas for probabilities, we would add, because this is another situation that could possibly work where I get a 4 just once. So here I want not a 4, then I want a 4, then not a 4 again. Okay, and then the last situation, I get not a 4, not a 4, and then I get a 4 on the last one. So if you take a look, it kind of sounds like all the probabilities for getting a 4 exactly once is the same, because when you multiply all these numbers together, you're going to get the same fraction overall. However, we do have to take into account that there's going to be different orders, so really we're multiplying this by 3, because there's 3 of these different probabilities that we can find, but the overall probability when I multiply all my fractions together, I get 25 over 216. So my final probability is going to be 75 over 216, and I believe this comes out to be like 34%. Actually comes out to 0.3472. Okay, so this is my example of a binomial probability, and so let's actually define a binomial random variable. So binomial means that there's only going to be 2 outcomes, success or failure. And then in these 4 rules, I tried to make it so that you have like an acronym. So the first one is B for binary. The second one starts with an I, independent trials. So between each thing that we do, like in the previous example, I rolled the die 3 times. So in each of those rolls, they have to be independent of each other, which makes sense. When you roll a die, it's not like the die remembers what you rolled the first time or anything like that. So each event there are independent. The third rule is that there has to be a set number of trials. So n trials. We call that number of trials to be n. That's going to be the variable we use. And so like for our example, we were rolling the die 3 times. And so that was n. And then the last rule is that the probability of success has to be the same for each trial. So when we talked about success or failure, we were saying, in my example, a success counted as rolling a 4. So a failure was not rolling a 4. The probability of success was 1 out of 6 because the probability of rolling a 4 is 1 out of 6, and it doesn't change from trial to trial. So out of the 3 trials, that probability stays the same. This is different than if we were doing something like picking cards or whatever out of a deck and you didn't put it back in, then the probabilities would or the events would be dependent, so the probabilities would change. And so the independent trials and the same probability for each success kind of goes hand in hand. So in our example of rolling the die 3 times, as a random variable, this is what it would look like. We could define x, capital X, to be the number of times we land on a 4 out of the 3 rolls of a die. So the probabilities that we could find with that could actually vary. All the different outcomes of x would be from numbers from 0 to 3, because the least amount of successes that we could get is 0, meaning like out of 3 rolls, we don't land on a 4 once. So all of them are numbers other than 4. We could land on a 4 once, we could land on a 4 twice, we could land on a 4 3 times, because that's the maximum. So out of 3 trials, the maximum is always going to be the same number as your total number of trials. So finding these probabilities, we can do this the long way. So we can actually just write it out and multiply all our fractions together. So getting 0 successes means that I'm going to need a failure, and then another failure out of my 3 rolls. There's no other orders that I could do this in, so my probability for my random variable being 0 is just going to be 125 out of 216, which comes out to be 0.5787. So basically like 58%. Then if I were to find the probability that x equals 1, meaning I roll a 4 exactly once out of the 3 tries, we did that earlier with this, where we wrote it all out. So we got 34.72% from that. Then that would mean we get we roll 4 twice out of our 3 rolls. And again, I can do that in 3 different orders. So if I just list out all of my different ways to do this, I can get a 4 the first time, a 4 the second time, and then not a 4. Or I can do a 4 the first time, not a 4, and then a 4. Or I can do not a 4 first, and then a 4, and then a 4. I'm pretty sure that's all the different orders to do it. Okay, so that probability is going to end up being, so there were 3 orders to do this, times, and I'll just kind of write this out a little bit differently, because it looks like in each of my probabilities, in each of the parentheses, I have 1/6 twice and 5/6 once. And there were 3 of them, so that's why I multiplied by 3. That probability is going to end up being 0.0694, so almost 7% of rolling a 4 twice. Okay, and then the last one for getting a 4 all 3 times, then the probability, there's only one way to do this, would be to get a 4, and then a 4, and then another 4. So that probability ends up being 0.0046, or not even 1%. I mean, that makes sense because it's pretty rare to get 4 3 times in a row. So if you were to add up all our probabilities for our 4 different outcomes here, you should get 1. So again, if you think about this as like that little chart we made for the probability distribution, we would have our x values on top, our probabilities on the bottom, and it would just be for x equals 0, our probability is 0.5787. For x equals 1, it would be a probability of 0.3472, and so on. So this is a probability distribution. It's legitimate because each of our probabilities are between 0 and 1. The probabilities add up to 1, and all our x's would make up all the different outcomes for our random variable of the number of times we land on 4 out of 3 rolls of the die. Binomial random variable, I want to talk about a faster way to calculate these probabilities. Rather than having to think about like all the different orders, let's actually use a formula, because if, for example, if I were to actually roll the die 10 times instead of just 3 and then count how many 4s I landed on, from there I could do way more different orders for this. And so that would just be annoying. The formula looks like this. So for any binomial distribution, the probability that our random variable x equals, and I'll just call it k for how many successes we want. The formula looks like this. So NCK is a combination. So if you think back, most people learned combinations and permutations in Algebra 2. If you didn't, it's okay. It's not like super important that you know where it comes from. I'll show you how to do it in the calculator, and then you'll have how to find it. But basically, it's a combination of how many different ways to get the number of successes that you want. So like when we were talking about the different orders of when we could get our successes and failures. So that just tells you how many orders you can actually do it in. This part of our formula, p to the k power. So p is going to stand for our probability of success for one trial. So like for us, when we roll a die like trying to land on 4, our p was 1/6. K is how many successes you want. So if you remember back in our probability of x equals 2 here, the very end, I tried to write it out like this so it matches the formula. So if you look, this was the number of orders we could do this in times our p raised to the second power, because we wanted 2 successes. That's what we wanted when we calculated the probability of x equals 2. And then so we have 2 successes, and then the third one has to be a failure. So 1 minus p in the formula would be the probability of a failure. So for us was 5/6 raised to the n minus k power. So n minus k just means like this is your total number of trials, n, minus how many successes you want, meaning the rest of your trials that weren't successes would have to be failures. So like for us, if we had 2 successes, then 1 of the trials would have to be a failure because we had a total of 3 trials. So that's how this formula works, and this will work for every single time. So this next part, I want to show you how to get this NCK in the calculator. So let's say I was trying to do NCK in the calculator for my x equals 2 probability. So N stands for my number of trials, which for us was 3. C is going to be done in the calculator, and then K is how many successes we wanted. So if I'm doing x equals 2, then K would be 2 for me. So because I need to start with N, I'm going to type in the 3 first, because that's how many trials I had. To get to the NCK part, or the C part in your calculator, you go to Math, scroll over to the right until you see PRB, and then it is the third one. So if I hit 3, it'll say, actually the calculator says instead of K it uses R, but same thing. So 3, NCR 2, because K for us was 2. We wanted 2 successes. And then when it calculates it, we get 3, meaning we have 3 different orders for us to do this in. Okay, so let's do an example together. All right, so in our example, each child of a particular set of parents has probability of 0.25 of having type O blood. Suppose the parents have 5 children. So right there, they're probably going to ask us about children having type O blood, so our success will count as having type O blood with a probability of 0.25. So P equals 0.25 here. And then it also says, suppose the parents have 5 children, so if we're talking about like how many children we have with type O blood, then N for us would be 5. To show that this is binomial, so that we know to use the binomial distribution formula for probability, we are talking about binary, success or failure, so having type O blood or not. Independent events, or independent trials, sorry, means that for each child it should be independent from the next, which makes sense because having a child first isn't going to affect the blood type of the second, and so on. The third rule was that we had to have fixed number of trials, so n trials. Here we have 5. We're only having 5 children here. And the last one was that the probability of success has to be the same for each trial, which it's 0.25. Okay, so sometimes you'll see the way to write this to show that this is binomial and listing out all the important information. You'll see it written as capital B parentheses n comma p. So if you ever see this notation, it's just telling you it's binomial. This is what n is. This is what p is. So for our case, for this example, it would be binomial where 5 is n and 0.25 is p for the probability of success. Okay, so if you ever see it written that way, that's all it means. So part A, find the probability that exactly 3 of the children have type O blood, meaning we're looking for the probability of 3 successes. So we are trying to calculate where x equals 3. Okay, so writing our formula, if we have n is 5, we want 3 successes, 5c3, times the probability of success, which was 0.25, and we want 3 successes, so we're going to raise that to the third power, times our probability of failure, so 1 minus p would be 0.75, raised to the 5 minus 3 power, or 2. Okay, so obviously I can calculate this out in my calculator from here, or shortcut in the calculator. Here we go. So if you pull up your calculator, we don't even need this NCR part. I just showed you that just so, like, in case you ever had to calculate just that part, it's there. But our calculator actually has a way for us to calculate this entire probability without any of these calculations. However, because this is a math class and on the AP test we have to show work, you're going to write this out filled in, the formula filled in, basically. But then to actually calculate things, we're just going to use our shortcut. So you're going to go second vars, and then if you scroll all the way down, you'll see Binompdf, Binompdf. So binom obviously just stands for binomial. These two functions also show you what the difference is between them, but for right now we're going to look at Binompdf. So when you hit enter, if you have the updated version of the calculator, it'll give you this menu. If you don't, then it'll just like bring you back to Binompdf of the main screen with the parentheses. And then these are the things that it wants you to type in, separated by commas. So it'll always start with trials, which for us was 5. N was 5 for us. P is our probability of success, which is 0.25. And our X value, so how many successes we wanted, was 3. And then I'm going to hit paste. So if you have a non-updated version of the calculator, this is going to be what you see. So Binompdf, parentheses, and then you're going to type in 5, 0.25, 3, and your parentheses. When you hit enter, it'll calculate that probability for you. So there's no other thing that you have to do other than just writing it out to show your work. So our probability is going to be 0.0879 as our probability of finding exactly 3 of the children that have type O blood. So for the next part, we were trying to find the probability that less than 3 of the children have type O blood. So keep in mind when we talk about less than 3, we are not including 3. So really, we're looking for the probabilities from 2, 1, and 0. So if you remember, the least number of successes that we can get is 0. So really, when we're looking for the probability that x is less than 3, we're trying to find the probability that x is 0, or the probability that x is 1, or the probability that x is 2. Okay, so obviously you can find each of these probabilities in your calculator using Binompdf, which is all nice and dandy. Just a little tedious because you got to type it in 3 times and then add your probabilities up. Or another shortcut, if we look at the calculator again. So when I go into second vars and down to Binompdf, right under it was Binompdf. The C stands for cumulative. So it's kind of nice because your calculator will actually add everything up for you, starting from 0. So if I use Binompdf and make sure at the top it says Binompdf, not PDF, because the menu basically looks the same. So you have to be careful which one you're actually using. We still have 5 trials. Our probability of success is still 0.25. Our X value here, whatever we type in is the number, the X value that the calculator is going to add up to. So I wanted to add up 0, 1, and 2, so I'm going to type in 2. Your calculator always starts at 0 whenever it does Binompdf, starts at 0, and adds all the x values up until the number you type in. So if I type in a 2, it'll add up 0, 1, and 2 for me. Paste, enter. So almost 90% is our probability for having less than 3 children with type O blood. Okay, so for the next example, we're looking for the probability that at least one of the children have type O blood. So at least one means that we want one or more. So really we're looking for the probability that x is greater than or equal to 1. So again, if you think about all the different outcomes for this binomial random variable, our outcomes could be 0, 1, 2, 3, 4, or 5, because 5 is our maximum number of successes that we could have, 0 is the least. So if I want greater than or equal to 1, basically I'm trying to add up the probabilities for x equals 1, 2, 3, 4, and 5, with 5 being the maximum. Or if you want to think about it as the only probability I don't want is 0, like I just want to make sure I don't have any children with type O blood. So if you think back a chapter ago, we also talked about like a formula for trying to find probabilities of at least one was 1 minus none. I try to make it rhyme so it's easy to remember. Finding the probability of at least one is the same as the probability of, or 1 minus the probability that x equals 0, because that's where we would have no children with type O blood. So again, if we just found the probability of x equals 0 here, we can subtract that from 1, and that'll give me the probabilities that I actually want, because 0 was the only one that I didn't want. And so using my calculator, because I'm just looking for the probability of one number, just x equals 0, I could use Binompdf. So second bars, I'm actually going to scroll up to get there faster. Binompdf, 5 trials, 0.25 is my probability, and 0 as my x value. Paste is 0.2373. I'm going to do 1 minus, and then second, and then the negative sign will copy paste the number you just got. Or if you don't want to do that, you can do 1 minus, and then depending on your calculator, it'll let you scroll up to highlight it, and then enter would copy paste it for you. That's kind of nice if you didn't know that. So our probability for at least one children having type O blood is going to be 0.7627. And the last part of our example, should the parents be surprised if more than 3 of their children have type O blood? Justify your answer. So the parents should be surprised if the probability is really low, right? Because that would mean it's kind of rare for it to occur. So that's basically what we're trying to look for then. What is the probability that more than 3 of their children have type O blood? So if I wrote it out in symbols, it would be P is X is greater than 3. More than 3 does not include the 3, so greater than. So if we're talking about more than 3, we're really adding up the probabilities for x equals 4 and x equals 5. Those are the only numbers where x is greater than 3. Or if you want to think about it, this is another way to write it out. We could do 1 minus the probability that x is less than or equal to 3. So a couple different ways for you to do this. If you were trying to add up the probabilities of x equals 4, x equals 5, you could do Binompdf of 4, Binompdf of 5, add those two probabilities together. Or the other way is 1 minus the probability that x is less than or equal to 3 would add up from 0 to 3 for you if you use Binompdf, and then 1 minus that. So for the greater than problems, you just have to think about like, what are you including? What numbers do you actually want? So depending on whether you want to use CDF or PDF, to me for this problem, both are a similar amount of work. So it's up to you which one you want to do. Sometimes though, you'll notice that like adding them all together, if n was a much bigger number, then it would be annoying to add everything up together. So sometimes it's easier to use CDF. But again, it's up to you. Neither way is incorrect, so whichever one you want to use. I ended up using Binompdf of x equals 4 and Binompdf of x equals 5, and I'm going to add these two numbers together. One thing I do want to point out, whenever you see a number like this in your calculator with an E in it, That's just scientific notation. It's just saying this decimal is going to be so small that your calculator decided to use scientific notation instead. So e negative 4 just means you're moving the decimal place 4 places to the left. So 1, 2, 3, 4 means you have 3 zeros in front of the 9. So it'd be like 0.0009765, blah, 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 blah. I'm adding that to my first probability for x equals 4. And then my final probability for this is going to be 0.0156. So knowing that, we need to answer the question, should the parents be surprised if more than 3 of their children have type O blood? So that probability is pretty small, which means that, yeah, we should be surprised if more than 3 of their children have type O blood, because that wasn't supposed to happen very often. So I would finish answering the question by saying, yes, the parents should be surprised because the probability of more than 3 of their children having type O blood is only 1.56%. All right, the last thing I want to talk about in this section for now is the mean and standard deviation of a binomial random variable. So we talked about how this binomial distributions are a random variable. So it's something where we can actually list this out as a probability distribution table where we list out all our outcomes for x and all our probabilities for each of those outcomes. So I just put ... n because depending on how many trials we have, that's the maximum number of successes that we could get. And we can find a probability for each of these using Binompdf. And so because it's a probability distribution, we can calculate a mean and a standard deviation like we did with our random variables. So if you remember, the mean was like you would take each of your x's and the probabilities, multiply them together, and then we would add them all up, and that would be our mean. So like on average, for that random variable, whatever we're trying to do, that's how many times it would occur. But the standard deviation was a slightly more complicated formula where we would take each of our x values, minus the mean, square it, multiply by the probability, and we're doing that in the calculator. With a binomial random variable, the formulas are actually much nicer because we already know there's like a set number of trials for them, and so it actually makes things easier. The proof for this is in your textbook on page 398 if you're like really interested in seeing why this works and why these formulas are the way they are, but you don't need to know it, so I'll leave that to you to look up if you would like. But the formulas look like this. So the mean of our random variable x, our binomial random variable x, is just n times p. So it's way easier to do because we don't have to like add things together or anything like that, meaning take the number of total trials that you have, multiply it by the probability of success, and that's how many expected successes that you should get in n trials. The formula for the standard deviation is just big square root of n times p times the probability of failure, which is 1 minus p. And so way easier to use than finding the mean and standard deviation of a random variable. So that's kind of nice. The interpretations for them are the same as the interpretations for just mean and standard deviation of a random variable. All right, that's all I've got for this section. We'll finish up the section in the next video, but thanks for watching. I know the sound quality was not the greatest here. I'm so sorry. I'm using a different camera because obviously I'm at home. So, but thanks for bearing with me. Have a good one. Bye.